All right, so in this video, I want to go over a couple complex projectile examples that involve a baseball being struck, and these are slightly different than the complex projectile skeleton problems that we did the other day, but the approach is the same. So we're actually going to start with number 4 here. And what I mean by the approach is we're still going to start with a drawing. So for number 4, we have a baseball player, Miguel Cabrera, that is going to hit a ball over an outfield fence, which is some distance away. I think in the problem they tell us it's 130 meters away. Now we can go ahead and label that delta x. But remember, we can, set delta x to be whatever we want, but if delta x is a certain value, then the time is a certain value that corresponds to that delta x. So in this problem, it's not the same as it would be, say, with the soccer ball problem where the ball is being kicked and we have the entire parabola. In this case, the ball might not take the entire parabola. In fact, the ball might not come back down until way after this outfield fence. So that's kind of what we're figuring out. They tell us that so once again, we'll keep with our drawing, that the initial velocity of the ball, we'll call this VI, you can call it V naught if you want, is equal to 44 meters per second. And it's hit 30 degrees above the horizontal. I'm going to put a little yellow right there. And that'll be my theta. So here we have a vector that's directed in the x and the y direction. And just like last time, one of the themes for these problems was to split this into components. So let's go ahead and do that we're going to work in each direction independently to solve this. So we'll call that VIX. And call this VIY. And because this is a x component and a y component, the angle between them is 90 degrees. Also notice that I put the two components head to tail. And that also makes sense because they're adding together to create VI. And but VI points up and right, and VIX should then point right, and VIY should then point up. I always draw them so my 30 degrees is inside of that component triangle that I made. What else do we know? We know the ball that Cabrera's bat connects with the ball 1.5 meters above the ground. Now, is this delta y? Not necessarily, right? Delta y is the change in the ball's position in that time period in the y direction. So it's more like the ball's initial position, yi is 1.5 meters. I'm actually going to come back to that later. So right now I'll just draw it in, and then we know that the height of the outfield fence is 3 meters. Once again, not labeling it delta y because that's the change in the ball's position. It's all about the ball in this problem. All right, and I think that's it. Okay. So coming back down here, so what we mean by the themes of the problem being the same is that this could be, this problem, what we're going to do is we're going to split it up into x and y components with the velocity, and then we're going to solve in one of those directions. Which direction is correct? Well, that's that's kind of based on what we know in the problem. So what I'm saying is last time we might have solved in the y direction first and then switched to the x direction using time as a bridge. This time we might use the x direction first, then go to the y direction using time as a bridge. It's really just about what you know in the problem. So you can't just say, "Oh, I'm always going to use this direction first." You can't. You have to actually think. And if you get it wrong because you guessed wrong, um, it's no big deal. You just get to a point where you're stuck, and then you try the other direction. So if one direction doesn't pan out, you get stuck, go to the other direction, and then solve. All right. So here, one thing we can do to get this problem started is label our right triangle. Across from 90 is our hypotenuse. Across from theta is our opposite. Next to theta is our adjacent. And now we can go ahead and solve using some SOHCAHTOA. Always write your formulas out. I'm just going to solve for the adjacent first. And you can just write a over h. You don't have to write the whole thing, but at least write that out so that way you remember. Because really you want to memorize these. All right, multiply both sides by 44. Whoops. All right. Cosine 30 is that square root 3 over 2 or 0.866. So I got to type that in really quick. It's going to be 38.105 roughly. Go out 2 or 3 decimals past, or 2 or 3 numbers past the decimal. Don't forget your units. VIX is a vector. It has units, it points. All right. Then we'll do the same thing for VIY. This time we'll use sine. Guess we could have used tan now that we know the adjacent, but I always do it the same way. I don't like to change the method just because I have one more piece of information. Sine 30 is the nice one. It's 1/2. So I'm going to go ahead and rearrange this. All right. So this is what's going to go in our K formulas, right? Because when we write our K formulas, they have VI in them sometimes, and that has to be, you write your K formulas either all in the X direction or all in the Y direction, so we need these values for the K formulas. All right, so which way do I want to work first here? Well, what's the question, right? I think the question is, does the ball go over the fence and by how much, right? How long does it take the ball to reach the plane of the fence? So we want to know that time value and how high is the ball when it reaches the fence. All right, here I really like the X direction more because we know a little bit more about the X direction than we did previously. And what I mean by that, if I can show you here. Well, the X direction is a little simpler, but we also know this delta X value, which is something we don't normally, or didn't normally have in the last problem where we just kicked a soccer ball and we didn't know how far it went. So I like the X direction here. If we were trying to find the time for the ball to reach the fence in the Y direction, it's a little tougher. And I'm not sure where to start with that because we don't know where the ball is going to be in the Y direction. For instance, it could take, let's see here, let me grab, say purple. The ball could take this path, right, and be at some negative delta y, which it really wouldn't be in the ground, but you get the idea, right? It would hit before the fence. We can't deal with bounces. We're not dealing with any impacts or forces with the ground. Our projectiles are just about what it does in the air. The ball could do this and just barely clear the fence. Well, that's a terrible looking parabola. Maybe I should try and draw that one more time. Okay, the ball could do this and not clear the fence. The ball could do this and go way over the fence. So we're seeing a lot of different options for what the ball could do, right? And that's kind of the point. When the ball reaches the plane of the fence, we want to know about that exact point. So we don't really care what happens after the plane of the fence, which is, we'll say right, draw this in orange, right here, right? Once the ball gets beyond that, we don't really care what happens. So anyways, I'm thinking the x direction is easier to work in. So let's give it a try first. And like I said, if we had tried the y direction and it was, or if we try the x direction and it's wrong, we'll just switch to the y direction. All right, so okay, so in the x direction, what do we know? We know VIX. Well, yeah, let's just go ahead and jot these down. And we know how far away the ball is, which is 130. Now, what we can use here, right, if we remember our K formulas in the x direction, the one that was useful was K2. Try and write that out. And we knew that projectiles don't accelerate in the x direction, left or right. They do right when they're hit by the bat, but our problem starts after the ball leaves contact with the bat. So that means that acceleration in the x direction is 0. This whole term here becomes 0, and we're left with this. So this is going to be nice, right? Based on what we know here. We can put that 130 right there. We can put the 38.105 right there and solve for t, right? So that's what I want to do here. Something like that, right? So divide both sides by 38.105. We're going to get t equals 130 meters over 38.105 meters per second. Notice what's going to happen with the units, right? Fraction at the bottom of our fraction, so we'll flip and multiply. Seconds is going to move up top. Meters are going to cancel. Get our calculator out for that. Did I write? I think I wrote that wrong. I wrote 150. My apologies. Type this in really quick. 3.412 or 3.41. We'll just go with that. All right, so we know this, that when the ball hits 130 meters, which is where the fence is, right? We don't know where it's going to be in the air. It could be in the ground. It could be way above the fence. It could be hitting the fence. But we do know that this will happen. It will hit 130 meters. at the time 3.41 seconds. And so this is going to be our bridge to work in the y direction and allow us to use our y formulas correctly. So this was the correct direction to work in first, just based on the fact that we have a simple, x is always a simpler direction, but furthermore, we know so much about the x direction, right? We already knew 2 out of the 3 variables, so it allowed us to solve for time. And time is what we want to bridge the directions, so it was perfect. All right, so let's go ahead and go to the y direction now. And we want to know the height of the ball. We want to know, technically, we don't even want to know delta y, right? We want to know yf at 3.41 seconds. That's what we really want to know. And so there's a couple ways to deal with this. Let's say you didn't realize this, and you were like, let's just solve for delta y. Well, let's go ahead and do that, right? I think we can do that, and so we'll just solve for this guy right here. Maybe you're thinking K formulas, and you're thinking K2, right? That's the one with delta y already on its own that we just used a second ago. We know VIY, we know T, we know AY. So I think this is going to work out really good for us, right? We know T obviously is 3.41 seconds. VIY, I think that was 22 meters per second. And we know AY, right? Projectiles do accelerate in the A direction, and that's downward. It's called downward negative. I don't think we stated that originally, but we should always state that. At negative 9.81 meters per second every second, right? Also, we can just write that as negative 9.81 meters per second squared. All right, so this is kind of what we know here. Put a line around this. Whoops, got the 2 in there. That's okay. All right, so let's go ahead and sub some of those values in down here. And we want to know delta y, we'll say. Delta y isn't technically right, but we'll come back to that. All right, 22. Time is 3.41. Notice how important this negative sign is. The reason why I say that, let's plug this 3.41 in here. The negative sign, what we have here are 2 things happening in this formula, if we think about it, right? One is that the bat is going to hit the ball upwards, and that's going to be the positive effect of the bat, and that is this right here, right? Then gravity is like, no, the ball is going to come back down, and gravity is saying that in red. So this is like the battle that's happening here, and we want to know which one's going to win out, right? The positive effect of the bat initially, which is in yellow, or the negative effect of gravity that is going to happen the entire time. Now, eventually, we know the yellow part's going to run out and gravity's going to win and the ball is going to come back down. Is 3.41 seconds, is it enough time for gravity to win that fight? And that's kind of what we're saying here with this formula and how it's working out. So we're going to have a positive number in the yellow and then a negative number in the red, and we're going to see what happens here. So let's go ahead and do a little math here. 22 times 3.41, I'm going to have to plug that in the calculator. is equal to 75.02. Units here are just meters, but you can see that because the seconds are going to cancel, and you're left with meters. And then we're going to subtract, right? Half of 9.81 is 4.905. So 4.905, negative 4.905 times 3.41 is equal to 16.726. I'm just going to go 16.73. Units here. Oh, ooh. You gotta be careful. I gotta be careful there. Hopefully you saw that mistake. Let me go back up and correct that. Right here, right? And that's tricky. There's been many times where I'll do one of these K2 problems and forget to square. So always square first. So let's slow down a little bit here. So we got negative 4.905, 1/2 times negative 9.81. Notice how the units actually saved me on that, right, from getting the wrong answer. Because I was like, oh, what about my units? I think I said that. Maybe I didn't, but that's what I was thinking. I was like, okay, how are these units gonna deal? And then I realized I left that square. All right, so 3.41 squared is 11.628. So 11.63. All right, and then we can go ahead and cancel seconds squared. And we're left with meters, which it has to agree with the 75.02, otherwise you can't subtract them. All right, so now we multiply that negative 4.905. I'm getting negative 57.04. And I have two, I gotta be careful with the signs. It should just be one negative sign there. So once again, that was negative 57.04 meters. All right. And then that, what's that gonna be? About 17.98. That's my guess. I better plug that in really quick. Yeah, okay. All right, so this isn't the top of the ball's parabola. This is just how high up in the air, or actually the change in the ball's y position at 17.98 meters. Is it how high up in the air the ball is? And the answer is no, it's not. And so let's look at why that is. So this is not the height of the ball, right? This is its change in y position. The ball didn't start at the ground, right? Where did it start? Is it 1.5? Yeah, 1.5 meters above the ground. So what this is saying is that delta y at this time is 1.5. Maybe I should get a different color here. Maybe red. It's saying that this is delta y. And this is 17.98. And that this distance right here, let's see, just go with black again. Right here at the bottom, if you can see me writing this is 1.5 meters. So our final answer is going to be 17.98 plus 1.5, which, what is that? Is that like 19.48? It's going to be 19.48 meters for YF. All right, So what we had to do there was add on, right, the initial height of 1.5 meters. Um, so a way around that, or a way to think about that mathematically, what I'm saying is this, that delta y is never height. Delta y is equal to yf minus yi. We know that delta y is 17.98 meters. It's equal to yf, which we want to know, minus 1.5 meters. We'll add 1.5 to both sides. Right, just doing a little algebra here. And we'll go ahead and get yf is equal to 19.48 meters. Another way to look at that would be in your K2 formula. On the AP test, let me rewrite this out. They don't actually give you this as the K2. What they give you instead most of my students don't like this version of it, but in this problem, it would have worked out better, right? Because what they did there is they split this delta y into yf minus yi, right, for that. Then they kicked this yi over to the other side. So over here you have plus yi, and it's solved for yf. So that is another way to write K2, another form of it that actually shows up on the formula sheet for the AP test. All right, good. All right, so there we have it. Pretty straightforward. Work in the or draw your formula, or draw your problem. Split any velocities that are in both the x and the y direction into their components, and then choose, and do that using SOHCAHTOA. Choose which direction to work in. If you choose incorrectly, then obviously pick the other direction. X direction was the one to work here first, just because I felt like we knew a little bit more with delta x and VIX. Had we have chosen the y direction first, we could have written K2 in the y direction, but we wouldn't have known time, and we wouldn't have known, we wouldn't have known time, and we wouldn't have known delta y. So we would have been stuck there, and we couldn't have used that, because for an equation, if you have one unknown, you can solve it with one equation. If you have two unknowns, you need two equations to solve it. So you couldn't have solved this with two unknowns and one equation. It wouldn't work. So we had to get a second equation from the x direction, solve that, get t, plug t in here, and then get our delta y. Delta y is not the final height. It is the change in y position of the ball. It's all about the ball. So we had to tack on that 1.5 meters and get a final answer here for our yf, or our height. This ends up being the height of the ball, but not the highest point, right? Not necessarily. It could be. We don't really know that. But this is the height at t equals, what was it, 3.41 or, yeah, 3.41 seconds. So this is the height at 3.41 seconds. Good. What else? Oh, finally, I want to make sure we answered the question, because we just went through and solved, but did we really get to the end? I don't think we did. I think the problem asks a couple things. How long does it take the ball to reach the plane of the fence? Okay, so we got that. That was 3.41 seconds. Then it says, how high is the ball when it reaches the fence? Okay, so we got that. That was the 19.48 meters. And does it go over the fence? And the answer is Yes, because the fence is only 3 meters tall. But a follow-up question, one more would be, by how much does the ball clear the fence? And then we could say, well, it clears it by 19.48 meters minus 3 meters would equal, was it 16.48 meters? So it would clear the fence by 16.48 meters. All right, and there you have it. Pretty straightforward. And once again, something that could show up, say, in the next problem, where you have somebody who doesn't know what they're doing in baseball, like me, hitting a ball, that the ball, its delta y value, is going to be negative when it reaches the plane of the fence. Now that means the ball is going to take a path in the next problem that's a little bit like this. It doesn't really mean the ball is in the ground, but what we can assume from that is that the ball falls short of the fence. So good luck with that, and have a good day.